Okay, so welcome everyone to the last colloquium of this semester. We are very happy to have Leonardo Rastelli here as our last speaker for this year, and he will talk about the conformal bootstrap. So please, we're happy to that you're here, and please go ahead and start with the colloquium. You probably should start sharing your screen.
Oh, I didn't. Sorry. Let's see. Sorry. Where is my Zoom? Share screen again. Here. Can you see it?
Yes, perfect.
Okay, thank you very much for the invitation. It's a pleasure to talk to this group of people. I prepared something which is for a broader audience than is probably necessary. I was just told that this is just theories, and instead I prepare what in the US is traditionally called the colloquium, which is for the entire department. But anyway, I can try to adjust the level of my presentation, even if the slides may be a little bit more elementary than necessary. So I'd like to give you a glimpse of what we have been doing in the last few years in combining this general program of the bootstrap. I will explain what that is, to this very ambitious goal of putting constraints on quantum gravity. And the program is still a bit in its infancy. The general bootstrap program is already quite mature, and I will start with that. But the application of the bootstrap to quantum gravity is really something that we just began to do. So let's see, I seem to be okay. So that worked. So let me start with etymology. So I was researching the etymology of the word bootstrap, as often the case with names that later on become, names of entire movements. You can think of many of those. It started as a derogatory term. So it started as, what is the metaphor? Of course, the metaphor, you're trying to pull yourself up by your bootstrap, which is impossible. And so it started this as a way of mock someone who was trying to do a preposterous task. But then the meaning changed in the American press in the beginning of the 20th century to mean instead that what you're trying to accomplish is, you're trying to help yourself without external aid. And in theoretical physics, this program has had several incarnations, but the general idea is that rather than trying to formulate a detailed microscopic model, as we often do in physics, you identify the correct degrees of freedom and write down a detailed Hamiltonian, then you solve it. Instead, you want to use as little external input as possible. That's where the metaphor becomes relevant. You're boosting yourself up in the sense of just using internal consistency requirements. So from Wikipedia, bootstrap is a self-starting process that is supposed to proceed without external input. And the modern incarnation of the bootstrap program takes a slightly different twist. Rather than trying to do this in the most ambitious way, which is to find the ultimate theory just by consistency, we have given that up. It's a slightly less ambitious program in which we think about the landscape of putative theories and try to carve them out, excluding theories that are inconsistent according to very general principles. And the principle, of course, as always is the case in theoretical physics, would be the general principle of symmetries and the rules of quantum mechanics. So this sounds preposterous. How can you make progress with philosophy? And in fact, you never can in physics. But the program becomes more concrete the moment we start to formalize a bit more precise what we mean by a theory. And so there are various incarnations of the program, and the one that has been so far most successful is when we specialize this notion of theory to be a conformal field theory. So what is a conformal field theory? I'm sure many of you are familiar, perhaps all of you are familiar, so I'll be quick. A conformal field theory is a quantum field theory which has, in addition to the standard symmetries of Poincare symmetry, it also has symmetries under angle-preserving deformations of space or space-time. So I'm going to discuss the two cases sort of in the same. And in some other case, of course, we're instead interested in time-dependent phenomena. For example, in particle physics, we want to consider scattering of particles, and the relevant notion is space-time. So, of course, if we have Lorentz symmetry, we can go from the two descriptions by Euclidean rotations from Lorentz to Euclidean time. So the formulation make manifest different properties, but essentially we can discuss them in the same context. And so a conformal transformation that locally looks like a rotation and a scale transformation. So I'm illustrating here this with this distorted. This is a square grid, it gets distorted. And so in particular, conformal transformation include the notion of scaling lengths. And as we're all familiar, most physical theories do not enjoy that transformation. Most physical theories have intrinsic length or mass scales. Most famously, gravity, of course, the Newton constant is dimensionful. Different lengths have intrinsic meaning. We cannot just assume that there is scale invariance. And so from that viewpoint, and of course, the same is in particle physics, elementary particles have masses. And so why should this be at all relevant to the real world? It would seem at first sight that conformal field theories are extraordinarily special, but essentially the opposite is true. Conformal field theories are central objects in theoretical physics. And one way to understand this is that you can take an extreme limit. For example, in particle physics, you can take the limit of very high energy. At very high energies, you can, it's permissible to neglect intrinsic masses. So the theory on very general grounds should become scale invariance at very high energies. And similarly, also at very low energies, again, you're taking an extreme limit in which you can neglect intrinsic scales. And so under rather general assumptions, one of the modern ways to think about quantum field theory, which is due to Wilson and many others, is that what is a quantum field theory? Well, it's essentially something that interpolates between a conformal field theory at very high energy and a conformal field theory at very low energies. And so you can really think of conformal field theories as like special points in the landscape of theories which are of particular significance. And first we should study those, and then we can connect the dots and study the rest of the landscape. And even before connecting the dots, conformal field theories are interesting in several physical applications, which are here I'm illustrating with these three cartoons. First of all, there's a very high energy limit of particle physics at the first cartoon. The second cartoon is a picture of liquid helium, and is meant to indicate something that we'll have a little bit more to say in a minute, which is the conformal field theories are very important. Well, they are the mathematical formalism to describe phase transitions. For example, the phase transition between fluid and superfluid helium. And finally, that is my third cartoon, they're relevant, for example, in condensed matter for quantum critical phenomena. And so finally, now we can say these words again. What is the conformal bootstrap? Is this very ambitious goal of compiling a catalog of all consistent conformal field theories, all quantum field theories that obey a certain axiomatic system, and have in addition this scale transformation and accompanying other special conformal transformations in all dimensions. So the subject already has quite a long history. In the early 70s, Polyakov and this Italian group formulated the basic requirements of conformal field theory. And the program had a fantastic success that many of you are very familiar with in the early 80s, with the exact solution of a large class of conformal field theories in 2 dimensions. In 2 dimensions, local conformal transformations are a much larger set because any holomorphic transformation will preserve angles. And so it's an infinite dimensional algebra that you can put to good use to find exact solutions, most famously the one of the 2-dimensionalizing model at a critical point. And the modern era, which is the last, I don't know, a little bit more than a decade, started with this famous paper by Rattazzi et al. That introduced this sort of, in some sense, more modest approach, which is rather than trying to find an exact solution of a given model, we retreat a bit towards this more modern idea of looking at the landscape of possibilities. We look at the landscape of possibilities and attempt to find what is permissible and what is definitely not permissible. And so we carve out theory space by the linear functional method, which I'm going to illustrate shortly. So let me start now with indeed the concrete example. Well, sorry, let me expand a little bit on the philosophy again. And the slogan that I will have over and over again throughout this colloquium is not anything goes. And so the idea is that, sure, the naively it looks like, you know, we are lost in this vast landscape of possibilities, and how are we going to ever find our way around it? But upon further analysis, it turns out that actually these very basic principles, symmetries and quantum mechanics, restrict even the a priori space of possibilities by a great deal. And so in some sense, even without doing any experiment, it turns out that pure thought can go a long way in narrowing down the space of possibilities. So that is sort of the philosophy here. We want to find what are the consistent theories, and then of course we need to look in the lab and see which one is actually realized. But even before any external input, the number of possible consistent theories is much smaller than you may think. And so the idea is that this is the way the bootstrap oracle works. It's a set of equations that I'm going to tell a little bit more later about, but for the time being, let's just stick with this cartoon, such that you start with a guess, a preliminary guess what the data of your conformal field theory should be. You ask this oracle, this Sibylla, illustrated here by this black box, whether those data can be consistent or not. And the oracle may say no, in which case, well, you have to refine your guess. Or it might say maybe, in which case you don't know whether your guess is correct, but at least you can keep going. And so the oracle never say yes. Saying yes is the old dream of finding an exact solution. That is sometimes possible, but often we have retreated to this idea of let's carve out theory space. And okay, so why is this useful? Well, this is useful because in some cases, the space of allowed possibility, the space of maybe is so narrow that in practice, it doesn't matter whether you have proof full consistency. The space of possibility is so narrow that is within experimental errors. And I'm going to illustrate this with a recent set of papers that used bootstrap techniques to make progress on finding the phase and the critical exponents for the liquid helium phase transition. So here is liquid helium again, and this is a plot of the specific heat as a function of temperature. So there's this famous divergence, this characteristic spike, which has the form of lambda. Lambda is not a COVID variant; it's just a spike of this of the specific hit. And this is actually a very, if you have never seen it, I invite you someday to watch a YouTube video. It's a very dramatic experiment to watch. It really makes you tremble. And if you see the phase transition from liquid, from fluid to superfluid helium. so there's the specific diverges with the characteristic exponent alpha, which I'm relating in terms of some other quantity delta S. For those of you who are familiar with the formalism of conformal field theory, delta S is the conformal dimension, is a scalar dimension of one of the operators of the conformal field theory, but if you're not, ignore it. And the claim to fame of this phase transition is that alpha is the best measured critical exponent in all of physics. The experiment is very difficult to do on Earth. Famously, this was done on the space station in 1992. It's a microgravity experiment, and probably this is the only good thing ever to come out of the space program, because everything else has been a huge waste of money. And famously, the experiment is in very dramatic disagreement with Monte Carlo determination of critical exponent. There's 8 sigma discrepancy, and so this controversy has been open for decades. And it has been recently resolved by the bootstrap. So let's look at this picture here. So here we can be a little bit more concrete finally about what I mean by theory space. So this is a 3-dimensional plot in which I am indicating 3 of these parameters that I was calling earlier conformal data. These are possible values of critical exponents. And you will recall that delta S was the quantity was related to the critical exponent for the divergence of specific hit. And so you can formulate a putative theory where these 3 numbers take any value you wish. In fact, this is just a 3-dimensional slice of an infinite dimensional parameter space that specifies the theory fully, but we can project it on this 3-dimensional plot. And so the idea is that to carve out theory space rather precisely means we ask the bootstrap oracle whether each of the dots in this space is allowed or not. And the bootstrap oracle may, if the bootstrap oracle say no, we discard it. If it says maybe, we draw a region. And so what is illustrated here, the green region is Monte Carlo results. This tiny blue region here, which you see is much more precise than Monte Carlo, is what the bootstrap oracle tells you. Only if you are inside this tiny blue region, the exponents can be consistent. So you see, although we have an exactly corner of the theory, for all intents and purposes, we are determining the critical exponent in a way which is more precise than Monte Carlo. Still compatible with Monte Carlo, and the gray region below here is the experiment. So the discrepancy has now been, the controversy has now been resolved in favor of theory. It means that the experiment was wrong, or either wrong, or they may have underestimated their errors. You know, it's hard to tell because no experiment like that is planned, and so for now we'll be content with saying that theory was right. Okay, so this is an indication of the power of these very general principles. What went in this calculation was very, very little. Probability are positive, conformal invariance, and the symmetry of the problem. The symmetry of the problem in this case is a U1 symmetry because of the phase rotation of the wave function for liquid helium. Pretty much nothing else went into this calculation. So I would say it's rather impressive. And now let me switch gears. So by the way, I should have said it, but feel free to interrupt at any time if there are questions. Maybe the level is a little bit too elementary, so I'll try to make it a little harder, but if there are any questions, of course, ask. So I'm going to now specialize to a slightly different version of the bootstrap idea, which with 2 goals in mind. First of all, it will illustrate a little bit more how this black box works, because so far I haven't given you any equations. I just told you there's a black box that tells you yes, can tell you, sorry, no, or maybe. And second, because it will be very relevant for when I switch later to quantum gravity. And so one of the simplest incarnations of the bootstrap is something which is specific to 2-dimensional conformal field theory, and it is the modular bootstrap. So we consider a two-dimensional CFT, which means one space and one time. And we would take the space to be periodic, a periodic circle, in fact, and time going vertical. So we have the theory on a cylinder. In fact, in 2 dimensions, you can map the cylinder to the plane by conformal transformation. So with no loss of generality, we can put the theory on the cylinder. And famously, the thermal partition function is given by doing the path integral over a region where we take time to be Euclidean and make periodic identification of period beta, where beta is the inverse temperature. So the thermal partition function is beta is doing the path integral of this toroidal region. One circle identified as the spatial circle, and another circle is the Euclidean time circle, which is related to the inverse temperature. And so the thermal partition function, as always, is the sum over Boltzmann weights of the energy of the system weighted by beta, e to the minus beta e. And here, this is a bit schematic. Of course, there could be degeneracies. The degeneracy are part of the sum. So it could be that the same energy occurs many times, but it's implicit in the way I take the sum. And the non-trivial consistency requirement, famously particularly powerful in 2 dimensions, I can now change my mind about what I call spacing, I call Euclidean time. I can rotate my head. And if I rotate my head, what was previously Euclidean time becomes space, what was previous Euclidean, what was previous space becomes Euclidean time. But since the theory is conformal, I can just rescale the radii as I please. And so all that matters is the ratio of the radii, which actually means that there is this remarkable high temperature, low temperature duality. The partition function should be invariant under sending beta into 1 over beta. And this is one of the discrete modular transformation, which gives the name to this program, the modular bootstrap. And there are really 2 constraints here in these 2 simple equations. One is this constraint beta going 1 over beta, which I will call from now on crossing constraint. It relates low temperature with high temperature. And the other constraint is that the sum over Boltzmann weights has to be with positive coefficients. Obviously, this is just the degeneracy of states, which is a positive integer, but we will forget about it. It's integer, but we will very much impose that it's positive. And the idea now is that there is a certain amount of tension between these 2 conditions. The fact that this should be a positive sum of this kind, and the fact that this condition should be obeyed. And this condition, by the way, it's an infinite set of conditions. For each value of beta, this must be satisfied. So it's easy to convince yourself that if you just give me a random collection of positive energies EI weighted by positive integers, this is just not true. Clearly, this is a rather powerful constraint on the possible values of the energy. And so that is where the bootstrap comes in. You give me a list of numbers, I plug it into this equation. If the equation is false, then the bootstrap alloc will say, no, go back to work. Now, in practice, of course, we need to be a little clever. And the way we're going to be clever is to milk these constraints. So I rewrote here the constraint as the sum over beta minus the sum over 1 over beta equal to 0. We're going to milk these constraints by applying a suitably judiciously chosen linear function. The linear function can be expressed as taking derivative with respect to beta, 2n plus 1 derivatives, the even number of derivatives vanish just by symmetry, evaluated at the self-dual point beta equal to 1, with, at this point, arbitrarily chosen coefficients alpha n. So if, of course, if the black equation is true, then the equation where I further take the derivative is also true. And the idea is that by a judicious choice of these alpha n's, we can extract more easily the consequence of this equation. And so that's where the art of the bootstrap goes in. You have to construct suitable functionals to judge whether or not your spectrum is consistent. In particular, you can construct functionals that answer different physical questions about the spectrum. Any questions about this? So this is the simplest mathematical illustration of this black box that I had earlier that would tell me whether or not a given set of putative data is consistent. Okay, so after this lengthy introduction, we can now go back to the main topic of the talk, which is, can we try to apply these ideas to quantum gravity? And again, the slogan is the same. Not anything goes in quantum gravity. And what do I mean by this? Well, we know, of course, at low energy in the real world, we have Einstein gravity. And the basic idea is that Einstein gravity surely is not the consistent theory of gravity. Something will have to happen at high energy to make it consistent. The theory is not normalizable. And nevertheless, it's a perfectly good effective field theory that we can think of in a derivative expansion. So this is very schematic. At low energy, I can think of the theory of gravity as the Einstein-Hilbert term plus higher derivative correction, which are being very schematic about, and then perhaps as matter fields, such as a scalar field, again, with its own set of higher derivative corrections. And so given an effective field theory of this very general kind, which is a choice of matter content, a choice of interactions, we believe that generically this will not be consistent. It's not possible to get this effective field theory as a low energy limit of a fully consistent theory of quantum gravity. This has a funny name, which is a swampland program. So the idea is that the swampland is the set of effective field theories that are inconsistent. And instead you want to be on the dry terrain of consistent theories. And this is a particularly apt metaphor in the context of the bootstrap, because it's a figure of the Baron de Munchausen, who was the first bootstrapper. So the metaphor of the bootstrap actually started with the Baron de Munchausen, who was trying to pull himself up not by his bootstraps, by his pigtail from the swamp. And so it's particularly relevant in the context of the swampland program. And there's been lots of papers in the string phenomenology community where the approach is a little different. So what swampland people do in string phenomenology is they look at string theory solutions, and by looking at those, they attempt to find some general patterns of theory that should be consistent. But our aim here conceptually is quite different. We don't want to assume anything about string theory or any concrete model. We just want to ask on very general grounds, without making any assumptions other than the very general rules of quantum mechanics, whether or not such an effective field theory has the possibility of being consistent or not. So that is the paradigm. And then a very natural thought comes immediately to mind, which is, well, this is a larger group of theories, so I hardly have to emphasize this point, but surely, even if you were in a theory, you have been to a number of colloquia where you have heard about the holographic correspondence, where quantum gravity in anti-de Sitter space, which is this very symmetric box, it's a space of constant negative curvature, is entirely equivalent to conformal field theory on the boundary. So this is a cartoon. This is a three-dimensional cylinder. The interior of the cylinder is three-dimensional anti-de Sitter space. And the boundary of the cylinder is this two-dimensional cylinder that I was mentioning earlier. Its spatial direction is this spatial circle, and the horizontal direction is a spatial circle, and the vertical direction is time. And so for quantum gravity in anti-de Sitter space, we get to rephrase the question of consistency precisely in the framework of the conformal bootstrap. So we can just now simply use the technology of the conformal bootstrap to answer these questions about quantum gravity in anti-de Sitter space. Towards the end of the talk, I will try to tell you something about flat space. And so here is a cartoon of scattering inside the bulk of anti-de Sitter space. We can think of excitations on the field theory boundary by inserting operators. So a 4-point function of 4-dimensional operators in the boundary, suitably chosen operators in a suitable kinematic limit, can be used to describe bulk scattering. And the original hint for holographic correspondence, of course, is very old. It came from the 70s, from this work of Bekenstein and Hawking. Bekenstein was just using thought experiments. Hawking did a more concrete calculation. And the idea is that black holes that in classical general relativity are perfectly fictionless objects, famously you just give me the mass and angular momentum that specifies the solution, appear to carry a very large entropy. And the entropy is the scales with the area. So that's a hint for holography. The number of degrees of freedom goes like the area, not like the volume. And it's the area in Planck units. And so here is this famous picture that was all over the place, which is some sort of photographs with lots of caveats, and sort of a first picture of the M87 black hole. And if you plug in the numbers, the event horizon of the radius of the event horizon of the M87 black hole is 120 distance of the mass to the of the distance from the Earth to the Sun. And so if the entropy comes out to this huge number, not surprising, of course, because it's an astronomical size object and we are divided by the Planck length. And so black holes carry a huge amount of entropy, which should be interpreted quantum mechanically as a large number of microstates, and the number of microstates grows like the area, suggesting some sort of a hologram description. And so we can now make the story more concrete, tying the two themes I had earlier by focusing on three-dimensional gravity. And so in three-dimensional gravity, by this holographic correspondence, we can really attempt to answer the questions of what is the space of consistent theories by studying the dual two-dimensional conformal field theory. Of course, three-dimensional gravity is a bit of a toy model because there's no propagating bulk gravitons. Nevertheless, if you put the theory in this very symmetric box, which is three-dimensional to the zeta space, there is a little bit of dynamical gravity left, which we can call boundary gravitons. In other terms, there are diffeomorphisms that do not vanish sufficiently fast at infinity that really change the theory. That should not be understood as gauge transformations. And for those of you who know these things, these are to be understood as Virasoro descendants of the vacuum. And so there is a little bit of dynamical gravity left in the sense of these boundary gravitons. And here is the action of three-dimensional anti-de Sitter 3 gravity with this negative cosmological constant. And then the question that we are trying to answer, what are these dots? What are the possible choice of these dots, of the possible completion of a model that at low end it just looks like pure gravity? And again, not anything goes, but what are the possibilities? And in particular, to make the question a little bit sharper, can we ever dream of having a theory of pure gravity? Or perhaps we need supersymmetry, string theory, or whatnot. And what would we mean by pure gravity? Well, surely we should have these boundary gravitons that just come along for the ride in the moment you have Einstein-Hilbert action. But clearly that's not enough, because as it turns out, this even in 3 dimensions, despite the fact that there's no bulk dynamical gravity, there are very legitimate black hole solutions, not unlike the ones that I was showing earlier, that have an entropy. And so these black hole solutions are then a clear hint that we should have, in addition to boundary graviton, we should have some sort of very massive microstates that give a meaning to this large entropy of the black hole. So the black hole solutions will have a entropy that scales like, okay, this curly L is the characteristic length radius of anti-de Sitter space. You see its length, curly L as units of length. And so the black hole entropy on dimensional analysis grounds will scale like L over n Planck. And in 3-dimensional gravity, L Planck is just a Newton constant. And if we're assuming, as clearly we should, that the system is weakly coupled, I mean, otherwise what are we talking about? So we're trying to find constraints on a theory that in the bulk looks like more or less like semi-classical gravity. We're attempting to make it to give a conformal field theory interpretation to something in the bulk looks like semi-classical gravity. So we need to assume that the Newton constant is small compared to the length scale of anti-de Sitter space. And so clearly we have a very large entropy. And this very large entropy has to come from some additional degrees of freedom on top of the boundary graviton. And so we can now rephrase the question a little bit more precisely. What is the purest theory of gravity? What is the theory of gravity in 3 dimensions that only contains boundary gravitons and the microstates of black holes and nothing else? So we are sharpening the question in a way that can be answered mathematically using the tools of the bootstrap. And notice, by the way, of course, that L over G is also, up to a factor of 3/2, the central charge of the two-dimensional conformal field theory. This can be computed by looking carefully at the algebra of these boundary excitations. Okay, so questions about this? Okay. And so finally, clearly now we can combine the ideas I had earlier in this little cartoon, where give a very precise formulation of the question, what is pure gravity? What is the purest theory of gravity? We think of the model of three-dimensional gravity now from the boundary viewpoint. And from the boundary viewpoint, it is just a quantum mechanical system. It has a Hamiltonian. It has a Hilbert space of states. Among these states, there will be the vacuum. On top of the vacuum, there will be these small ripples of boundary graviton. Those are the Virasoro descendants of the vacuum. And then there will be a first non-trivial excited state of energy E1. In the language of conformal field theory, there will be a primary state of the conformal field theory. So it's not a descendant of the vacuum, it's actual new primary of the theory with energy E1. And now we can ask the question very precisely. For given central charge, which eventually we want to take to be very large because we're interested in semi-classical gravity, what is the highest possible value of E1? Can we take E1 all the way to infinity for fixed central charge? Well, it's easy to see that that's impossible. And in fact, it's easy to convince oneself that for given central charge, there will be a maximal value of E1, which will be a certain function of the central charge, which I'm calling here E gap as a function of C, because if we exceed that bound, the modular equation Z of beta equals 0, 1 over beta cannot be satisfied. It's easy to see that if you just take descendants of the vacuum, that does not give you a modular function. So this is something that was sort of known before, but Hellerman made it very quantitative and proposed to study this by numerical methods. And so here is, again, a cartoon of what I'm saying. Omega is the vacuum. So here is a space. It's a cartoon of the Hilbert space of the theory and its energy. There's a vacuum, this ripple of boundary graviton, which are Virasoro descendants of the vacuum. And then the question is, how high can we push the first primary state E1 compared to the black hole threshold? We can compute the mass of the lightest black hole, and that has mass that scales like C over 12. And comparing this black hole threshold with the mass of with the gap tells us how pure our gravity model is. Of course, most theories will have a primary state becomes much earlier than the black hole threshold because we could have additional matter fields, supersymmetry or whatnot. But now the question is rather sharp. How high can we push E1? Can we push it all the way to the black hole threshold or even higher, or what is going on? Okay, so now the good news is that we get to use the bootstrap oracle in the way that I formulated earlier. And the bootstrap oracle is something that we can put on a computer using linear programming or semi-definite programming methods. And we can get estimates for this gap for finite value of the central charge, and also if we're interested in asymptotically large value of the central charge. And something very striking happens. There's a complete unexpected surprise. For two magical values of the central charge, which is 4 and 12, the spectrum so first of all, this E1, and not only E1, it turns out that this method, once you optimize, for example, the value of the first energy state, then the energy of the first state, then You get very precise estimates also for the additional excited state situated, etc. The spectrum, not just the spectrum, but the degeneration of the state converges to integers. And for example, for C equal 12, the gap is with extraordinary accuracy given by 2. And the degeneration of the first excited state is this famous number, which is 196,884, which is famously 196,883 plus 1. This is the famous equation that gave a hint for moonshine, because this number, 196,883, is the smallest representation of the monster, which is the largest sporadic group. And in fact, the full partition function turns out to be a holomorphic modular function. So there's something very magical going on here, because nowhere we impose holomorphic, nowhere we impose integrality of the degeneracy. So there's a hint of math and a hint of magic that come as a big surprise. For the question of weakly coupled gravity, we're particularly interested in C to be large, and then here we get to estimate the gap as C over something like 9. So C over 9, of course, is a little bit bigger than the black hole threshold. So that is slightly disappointing, because what we would have wanted is the bound to go all the way down to the black hole threshold. In other terms, we would like to prove by these methods that yes, there is a theory of pure gravity, and the gap precisely coincides with the black hole threshold. But of course, this particular constraint that we impose is just one of many additional constraints. We're just imposing modularity of the torus partition function. There are many other constraints that we can impose, and I will have something more to say about this.
Sorry, I have one question. So is it easy to see why this is just a linear relation between E gap and why it goes like C?
Yeah, it's fairly well. There's no okay. From the point of view of black hole thermodynamics, is sort of clear, right? It should correspond to the black hole threshold. I don't have a. It's of course sorry. This is just the leading term, right? I mean, of course,
yes.
As a function of C, this is a complicated function of C. I don't have a terribly good intuitive reason to, but of course it's consistent with what we expect from other
yes.
thermodynamics. Yes. Okay. And now comes the third. So I told you about the bootstrap. I told you about quantum gravity, and here comes a third player in my little tale, which I will connect at the end. So let me now switch gears completely and tell you about the sphere packing problem. So bear with me, eventually we'll all come together. So what is the sphere packing problem? It's a famous problem in mathematics, which asks what is the densest configuration of identical spheres in the Euclidean dimensions. So this is a deep question which has connections to modular forms, number theory, cryptography. Has only been solved in this very sporadic set of dimensions. What's peculiar about this problem, it takes a different flavor in any dimension. If you're solving one dimension, you go to one dimension higher, you're out of luck. The problem takes a completely different flavor. So of course, in one dimension, there's really not much to do. You're just stacking one segment after the other with no interval. In two dimensions, there's an immediate guess for what is the densest configuration of coins on the plane. Is the famous that should be centered on this hexagonal lattice. And so this is elementary, it can be done by elementary geometry, but actually it's a little subtle. So a complete proof only came in 1940. In three dimensions, it's also not very hard to guess what is the densest configuration of oranges, is the one you should, or cannonballs is the obvious one in which you should stack them. Actually, if you think a little bit about it, there's a regular lattice configuration, which is the one illustrated here. But once you have put oranges on one stack in the first slice, you can translate the second slice and then translate a little bit the third slice, etc., in a way that in principle has no periodicity whatsoever. So there's actually infinitely many equally dense configuration of spheres in 3 dimensions, as dense as the regular cubic center phase lattice. And the idea that this should be the densest configuration is sort of intuitive. It was made as long ago as 1611 by Kepler, and there's actually a little bit of interesting history here. Sir Walter Raleigh, who was this colorful character in England at the time, was doing commerce and war with the Americas, was interested in a precise formula to count the number of cannonballs that you could put on a ship. So he asked his mathematician friend Thomas Harrod to compute it, and that was not a very difficult calculation. But then Thomas Harrod got interested in the problem, and he was a friend of Kepler, and so he wasn't corresponding with Kepler. Kepler got very interested in this problem of discrete geometry. So here is a picture from Kepler's paper on the 6 corner snowflakes. He wanted to prove from first principle why snowflakes take the form that they have. That he didn't succeed, but in the process he made the conjecture that this is the densest configuration of spheres, and the Kepler conjecture was open for centuries. It was proved by Hales in 1998, and Hales' proof takes hundreds of pages, makes heavy use of computers. It's important in the history of mathematics. Was the first proof. After he proved it, of course, people were sort of convinced, but then he said, okay, well, you really want to be convinced, I'm going to give you a certificate that the proof is true by the rules of formal logic as implemented in a computer. So Hales' proof is the first non-trivial theorem. Not, of course, you can do this with trivial theorem, but the first truly important theorem that was proved, I don't know, in the early 21st century by formal logic on a computer. And so it came as a big surprise when on Pi Day in 2016, Marina Wiazowska posted on the archive a very short, very elegant proof that in 8 dimension, the densest configuration of spheres is the one given by putting the spheres on the centers of the EA lattice. And the proof instantly generalized to 24 dimension. A week later, with some collaborators, it was proved that in 24 dimension, the optimal configuration of spheres is given by the Leech lattice. So how did the proof go? Well, now hopefully things will start to come together. This will start to ring a bell. So Wiazowska built on an approach that was formulated a few years earlier by Kohn and Elkis. And what this gentleman showed is something which really is very much in the spirit of the bootstrap. They said that if you can concoct a certain function f of r is the radial distance. You should think of f of r as essentially giving you the density, the radial density of spheres. If you start from one center where we put one sphere, you go radially. And this f of r has certain positivity, moreover certain Fourier properties. It has the Fourier transform have to obey certain properties. Then this function provides an upper bound on the density of packings. And the upper bound is shown here as this red curve in various dimensions, whereas this jagged curve given by these blue dots are what, to this day, the best known packings in any given dimension. So, of course, in one dimension, it's clear enough. In 2 dimension is the hexagonal packing. You sort of see that the bound of Kohn and Elkis, which you can compute very accurately on a computer, is clearly not optimal in any dimension, because in 3 dimension, we know from Kepler and Hales that the cannonballs provide the best packing. Nevertheless, that doesn't quite saturate the bound of Kohn and Elkis. So the bound of Kohn and Elkis is just a necessary condition. It's very much in the spirit of this black box that tells you no or maybe. And in this case, 3 dimension, it tells you maybe, but the actual answer is strictly better. And then the other 2 striking features of the plot is that in 8 and 24 dimension, the blue dots corresponding to the Yates and Leech lattice are precisely saturated the Kohn-Elkis bound. And so essentially from a physics, this is also an interesting sociological difference between physics and mathematics. Kohn and Elkis had shown with extraordinary numerical accuracy that E8 and Leech lattice saturated this bound. And so, from our perspective, that's a proof. But actually all the credit goes to Wiazowska, who actually proved it, not numerically, but analytically. And the way she did it was by just exhibiting this function f of r analytically. And so the way she did it was by very clever ansatz that you know, as a certain Laplace transformer, certain modular forms, she was able to fix the modular forms by the Fourier properties and just exhibited the magic function that saturated the bound for d equal 8 and 24. That's a proof that the E8 and Lichlet and that the Kohn-Elkes magic function f of r is the same thing up to change of variables and renaming of this linear function. Of this linear function that I was indicating earlier for the modular booster problem. Okay, there's a little bit of fine print. More precise, the Kohn-Elkes problem is not quite dual to the problem of pure gravity that we're most interested in, but you have to introduce some additional gauge fields, 1 to the c. But there is a version of the Kohn-Elkes problem for pure gravity, which is really very much the same. But if we stick with this problem with additional gauge field, then we can establish a precise dictionary where studying sphere packing in d dimension is the same as the modular bootstrap with central charge d over 2. And the density rho maps to the energy of the first excited state according to this formula. So in mathematicians are interested in maximizing the density, we're interested in maximizing the gap. And in fact, rather curiously, Dalimil-Masac in 2016, he was actually studying yet a different problem, which is the crossing symmetry problem in one-dimensional CFT. That turns out to be also mathematically equivalent to the modular booster problem. And he had proved optimality of certain simple one-dimensional CFT in 16. And if you translate his linear function, you find precisely these magical modular functions that Jaszowska had. The physics approach is actually simpler because once you make this change of variable, the magic of modularity is largely gone. There's a very simple answer that Dalimil had formulated, which reproduces Jaszowska's functions. And so one of the really intriguing and curious feature of this correspondence is that studying the question of pure gravity, which requires us to take large central charge, gets mapped to the problem, what is the densest configuration of spheres in a very large number of dimensions.
Sorry, Leonardo,
yes.
Just a quick curiosity, but how does this translate? Or I don't know, if you know, are there any arguments on this d infinity, for example, like, because it looks like this Kohn-Elkes asymptotes to some finite value, or they just don't know what happens? Like in the previous slide, if you look.
Sorry, yes.
Oh, sorry, no, when you were showing this, yeah, this one. When D goes.
I should say that the correspondence, what we're actually showing here is that the linear programming problem that we need to solve for this modular bootstrap black box is the same as the linear programming problem that Kohn and Elkes need to solve to show this, to find this smooth red curve bound.
Yeah, I'm just wondering.
You could ask whether there's a deeper correspondence with the physics of gravity and the property of sphere packing. That is an excellent question. I will end with that. But at this stage, this is just at the level of the kind of optimization problem we need to solve. And the two optimization problems.
I understand that the packing problem is just module-like response is a big problem on its own. I understand, yeah. But I'm just wondering, like, you know, on these two sides, if I say my central charge is infinitely large, do I understand what happens on their side?
Well, you understand in the sense that well, sorry. In both cases, the problem is open. So we don't know what is the optimal bound for large central charge, and we also don't know what is the optimal density for large dimensions.
Okay,
So
there are just discrete
problem,
arguments and nothing else. I see.
So the problems are open on both sides. What's interesting is that they get related. So this part, and there are two layers to the question. So first of all, this is just one particular necessary condition that both the sphere packing and three-dimensional gravity need to satisfy. Of course, there are many more. But even if we just stick with this simple looking necessary condition, we do not know the optimal bound.
Sure.
So even at the level of just this simple constraint, there's no, we do not have yet a mathematical answer for what is the coefficient in front of C for large central charge.
Yeah.
Or in terms of this, in terms of the mathematician, probably what is the coefficient in terms of the how does the density scale for the even just the level of this asymptotic behavior of this red curve. So that seems like a problem that we ought to be able to solve. I mean, it's a very concrete equation. Mm-hmm. Nevertheless, it's not easy. Okay, so so in the last 3 minutes, and because I'm running out of time, let me tell you what we're doing more recently at the level of trying to apply this to flat space. Of course, there's a sense in which you should be able to take the radius of ADS to infinity and turn this picture of scattering in ADS into a picture of scattering in flat space. And this is an even older subject, the S-matrix bootstrap in the 1960s, where you want to constrain the amplitude as a function of modulus and invariance S and T, so subject to analyticity, crossing, Regge boundaries, etc. And this is hard because, of course, the analyticity property of the S-matrix have never been fully spelled out, or to be more clear, they have been spelled out, but it's not all clear that they've been spelled out correctly. And so carefully taking the limit from the finite box is perhaps the way to go, because the moment you are in the finite box, then you are on the safer grounds of rigorous conformal field theory. But for the time being, we can be a little less ambitious and formulate very plausible requirements on analyticity and boundedness of this amplitude. And so this is an exclusion plot that came from our recent paper from last year, where we look at gravity coupled to a massless scalar, the kind of effective field theory that I had earlier. And you see here, we have this a priori undetermined coefficients of the higher derivative term, G2, G3, and G4. And this plot should be again understood as an exclusion plot. What is on the right of these curves is allowed, and what is on the left is excluded. And you see that, you know, for fun, we did this in various dimensions. We cannot quite do this in 4 dimensions because of the certain divergence, infrared divergence that prevent us to go all the way down to 4. But if you're in a sufficiently high number of dimensions, then we can play this rigorous exclusion game. And so this is interesting. Just from very general principles of positivity and boundedness of the amplitude, we get to carve out the space of effective field theories. And one particularly fun game to play, if you're a string theorist, is to try to apply this in theory with supersymmetry, in particular with maximum supersymmetry. And if you have maximum supersymmetry, then the leading, you can show that the leading higher derivative correction is R to the 4th. This is something which is very much studied in string theory. And we can put a rigorous bound on the leading R to the 4 coefficient in a weakly coupled theory of supergravity, which happens to be 3.000, which suggests that eventually we should be able to prove that it's exactly 3. And string theory does a little better. It's 2.4. So again, we hope to eventually be able to, you know, what is the dream here? Eventually prove that the only way to get a consistent perturbative theory of quantum gravity, maybe with supersymmetry, is string theory. So we could push the bound down to the 2 zeta 3, that would be progress in that direction. Okay, so let me give you some outlook and conclude. I had 3 characters in this talk. One was the bootstrap, in particular, its 2-dimensional version in the context of modular invariance for 2-dimensional conformal field theories. I had the question of black hole thermodynamics, and in particular, the question, what is the simplest theory of quantum gravity in 3 dimensions? And I had the mathematical problem of sphere packing, and it turns out that these 2 problems are intimately related to one another. We haven't answered the basic physical question of what is the simplest theory of 3-dimensional quantum gravity, but there is some insights that come from these equivalences, in particular, this insight that that question is related intimately to asking what is the density configuration of spheres in a large number of dimensions is very intriguing. And you already had some, as often is the case, connecting physics and math can have both ways. So for example, from using optimization techniques that were developed by bootstrappers, our colleagues have been able to improve for the first time in decades on the asymptotic density of sphere packing. Again, we know it's not optimal, but it's a little bit better than was done before. And as I've emphasized, there really is, this is just one point of contact between the 2 problems, that you could ask whether there is a broader set of relations between the 2 problems on both sides. And then I really had very little time for that, but the really ambitious goal moving forward is to develop some sort of bootstrap for quantum gravity, at least for weakly coupled theories in asymptotic flat space. And we have some preliminary results constraining higher derivative corrections in a weakly coupled theory of gravity. And again, in the context of ADS, this can be made rather precise. And in a recent paper, we showed with sharp inequalities that large NCFT with a large gap must be local in ADS, in the sense of that the higher derivative terms are suppressed with a precise numerical coefficient multiplying something that scales like inverse powers of the gap. And yes, so in the fullness of time, it would be, of course, nice to derive or at least make progress in these notoriously thorny questions about analyticity property of the S matrix by thinking about this limit more carefully. Thank you.
Okay, thank you very much for the wonderful talk.
And I will leave you with this quote from Kandinsky.
Okay, thank you. Are there any questions?
I have a general question, Leonardo.
Yes.
So if you go through the dimensions, I mean, it's obviously spectacular going from 2 dimensions to higher dimensions for conformal bootstrap. But as you know, in 2 dimensions, there was another one for integrable system, was a bootstrap for 4 factors.
Yes.
Is it going somewhere if I go to higher dimension? Does it have any analog?
It would be great. I don't know how to do it. So the bootstrap from factors, of course, was mostly for integrable.
It's only for integrable, yes. It's for, yeah. But it's a clear-cut conditions that if you have a form factor of operator of this dimension in integrable system, it has to satisfy, and there is a list.
Yes, in principle, of course, we believe that if you give me a conformal field theory, in principle, right? This is all in principle. If you give me a conformal field theory and you perturb it by some relevant operator, if you had infinite power, you should be able to compute what happens at low energies, and in particular, you should be able to compute let's assume the theory develops a gap. And so it has a bunch of stable particles that interact. And in principle, with infinite power, just from the UV conformal field theory data, you should be able to compute the low energy S matrix.
You mean conformal perturbations?
Better than that. Yes, maybe resum the whole conformal perturbation theory and actually find the full answer at low energies. This is, of course, what you can do in integrable models. You perturb the Eisenhower.
Yeah, that's
you
how
perturbize the model by whatever, by the magnetic field, and then there is a whole story of the Malological, etc., where you can compute the S matrix, etc. In principle, even in 2 dimensions, integrability should just be understood as a technical crutch, right? In principle, we think that even in an unintegrable model, it should be possible on, just from first principles, that if you give me the conformal data, you should be able to compute the low energy S matrix. Of course, in practice, we don't know how to do it. And so going to higher dimension, I think, is sort of similar to first, and I would suggest that first try to do this in 2 dimensions in non-integrable models, develop some sort of numerical technique. So people have started to do that. There is a community that is studying the S matrix bootstrap, especially in 2 dimensions, by more numerical methods. And in principle, you should be able to connect the UV conformal data to the full-fledged low energy S matrix, even in an integrable theory. But of course, you would have to resort to some sort of numerical approximation.
Right, but Smirnov was able to sum up that only for integrable case,
Yes, of course. But if you're willing to use numerical methods, then in principle, you could try to set this up even for an integral in the integral cases. Now, another thing that I can offer is that in higher dimensions, of course, we can, in general, it's going to be very hard, but in supersymmetric models, for certain protected observables, you may hope to make progress. So, for example, in 4-dimensional, let's say, even n equals to 4 or n equal to 2 theories, it's still very much an open question. If you give me everything I want to know about the theory of the conformal point, there's no algorithm, as far as I know, to compute the masses of the BPS states on the Coulomb branch. These are 2 independent set of data that in principle are related to each other, because if I know everything about the theory, say the theory of the conformal fixed point, I should just be able, in principle, to turn on a VEV for my scalars and compute the masses of BPS states away from the conformal fixed point. But in practice, we don't know how to do that. We have indirect techniques to compute each of them, but a clear way to go from one to the other is or if you want, if I know everything about Seiberg-Witten theory and the whole spectrum of BPS states, that is not enough information to compute the dimensions of operators at the conformal fixed point. So clearly there is a relation with 2 sets of data, but we don't, and even for these very protected quantities, we don't quite know how to relate them.
Well, as you know, there is another there's something in 4 dimensions in n equal to. If you take n equal to star and send mass to infinity, you get pure n equal to, which is not conformal.
Yes.
So in principle, there are some tricky limits that you can take in conformal theory and get something about non-conformal theory.
Yeah, but I was saying even yes, but that's of course going to be hard. I would say even the simpler question, just take a conformal field theory and break conformality spontaneously just by moving on the Coulomb branch. In principle, this is something that we ought to be able to do. Compute the masses of BPS states on the Coulomb branch starting from the conformal field theory data. But we don't quite know how to do that. There are hints. For example, there is this work of Cordova and Shah, where they were able to compute certain wall crossing invariants on the Coulomb branch and relate them to the superconformal index. But it's a completely magical formula. Nobody explained where it comes from. It's just an observation that there's certain quantities you can compute in terms of computing certain traces, tracing over the space of BPS objects, and that appears to agree with counting local operators at the conformal fixed point. So
I have one more question, but maybe others should ask questions. I'm sorry. I will ask maybe at the end. Thanks.
Thank you.
Any other questions?
So then maybe I ask my question. So in 2 dimensions, there is another funny thing, which is just maybe observation in a sense, which is take the conformal block and now think about it this way. In massive theory, you will have the R matrix with spectral parameter, which depends on spectral parameters, or S matrix. If you scale rapidities all together to infinity with the ratios being fixed, then magically it gives conformal block. So instead of saying that I go from massive theory to massless theory by some mass goes to 0 or something, you take all lambda i's and scale them by multiplying some alpha, which goes to infinity. And observation is that the homological S matrix would give you a conformal block, and actually you can even say for which theory it's a conformal block. And I kind of suspect that this is what in higher dimension we would call infinite momentum frame, right? When we take all the momentum to infinity, there has to be something in bootstrap which.
Sorry, there's a problem with my internet. Can you hear me?
Yes, sometimes you disappear.
Yeah, so I only heard you till you said you scale the lambda i's to infinity, and then I lost you.
So you take S matrix, take what's called the homological Fadeev relation, when you have the exchange relation with S matrix rather than R matrix. And it depends on rapidities, and then scale all the rapidities with one constant, let's say lambda goes to alpha times lambda, all lambdas, and then take alpha goes to infinity. So observation is that would give you constant R matrix. So you will get a braiding relation for conformal field cell. So going from massive theory to conformal theory is done by going to infinite rapidity limit.
Yeah.
And we know that such limits actually are important in, like if you remember in BFSS matrix model and infinite momentum frame and so on. There has to be something like that for higher dimensional bootstraps that relates S matrix bootstrap with a conformal bootstrap.
Yes, there has to be. There has to be. And
is it known? Is it known?
No, it is not known. It is not known. There are other things in 2 dimensions you can do. For example, in integrable models, you can compute the character, the vacuum character, or in fact any characters of the say the minimal models from the massive phase. You go on the massive phase by turning on a relevant deformation, a relevant integrable deformation, and then you do a certain counting of quasi-particles. This is work by McCoy and others, and this gives you what's called a fermionic representation of the character, which is different from the one that comes with plus and minus signs that comes from looking at the null states. It's very cute. So there are equivalent representations of this. They are also related to this Ramanujan identity. There are equivalent representations of the character that can be interpreted as counting quasi-particles in the integrably deformed massive theory. But yes, how to do that more generally in a non-integrable theory or in higher dimensions is not known.
Thanks.
Thank you.
Okay, so I have a small question about sort of parameter space that you curve out with these bootstrap conditions. So far, it usually seems to be you sort of get a bound which you can maybe make narrower if you increase numerically. But can you also, for example, get islands or sort of special points or?
Sorry, of course, in the conformal bootstrap, you very much get islands, right? So we had this. I started with this famous. I could have done it for the Ising model, but I did it. This little blue island.
Yes. So is it also something you see for gravity?
Yeah. So right. So yes, you do. The reason here that this region is non-compact is actually easy to understand. It's the point that since I'm not imposing any supersymmetry, there's no a priori relation between Newton's constant, which controls the strength of gravity, and the self-coupling of the scalar. Those are independent quantities. Their ratio is giving you this non-compact direction. But if the reason to do this with the scalar is just because it makes life easier. Throw away the scalar and just do this for pure gravity. For that, you have to study the 4-point function of gravitons, which is a bit of a headache because of polarization. But this upcoming work by Caron Youot and Simon Duffy will do precisely that. And then you would indeed find a compar region.
I see.
I see. So the non-compactness here is just have to do with the fact that I've added an extra particle, and the self-coupling of the two particles are unrelated. That's why you get this, the ratio is gives you this non-compact direction.
Thanks.
By the way, is Simeon's work on large spin and many other people work on large quantum number expansion somehow helps in the effective description?
Not in, I mean, maybe one day, but not immediately here, because here we're just looking at excitation of the elementary quanta, if you wish. So we're not inputting any large charge. Maybe there's a way to combine them, but I don't know. It seems like a different kinematic regime here. For example, if you just look at gravity, we're just looking literally just a scattering of graviton scattering. So I'm not sure large charges.
Well, rotating black hole with a large angular momentum.
Yes, that's right. Maybe you could try to incorporate that in that framework. Yes.
Okay, thank you so much. I have to go. Sorry.
Thank you.
Bye, Leonardo.
Bye.
Thanks. Bye.
Any other questions? Then if not, let's thank Leonardo again for a very nice talk.
Thank you very much.
Thank you very much. It was a really nice talk. And
Good luck, everybody.
thank you. Bye.
Bye.